So in today's lesson, we're going to learn about something that is referred to as the sine law or the law of sines. So, the trig that we've learned so far, where we can use SOHCAHTOA, works great. Sine, cos, and tan works great if you have a right-angled triangle, right? A triangle with a 90-degree angle in it. But the reality is that often the triangles that we're seeing do not have a 90-degree angle. So unless your triangle has a right angle, you can't use sine, cos, and tan. So that's a problem if the problem that you're trying to solve involves a triangle without a 90-degree angle. So for that reason, there are two laws that were developed: the sine law and the cosine law were developed, and we're going to look at the cosine law tomorrow, but today we're going to look at the sine law. So here it is. So before we get into the details of the law itself, which you can see right here, I want to first go through the exercise of properly labeling our triangle. So notice that it says for acute triangle ABC. So when you have an acute triangle, that means that none of the angles in that triangle exceed 90 degrees. Okay, so that means that all of these angles will add up to 180, but none of them will be greater than 90 degrees on their own. And so in grade 11, you'll look and see, well, what happens if we don't have an acute triangle? What if we have an obtuse triangle? But you can look forward to that next year. So remember, if we're going to label a triangle, the corners always get the capital letters, and the sides opposite the corner are often labeled with the lowercase version of that letter. So for example, if this right here is corner or vertex A, then the side opposite we would call little a, lowercase a. So then that would make the side opposite capital B. This side right here would be lowercase b. And then, well, the C is a little harder to show. So then what we do is we can translate that into a formula called the sine law, which relates the sine of a particular angle to the length of its side opposite the angle. So we can say that the sides and their angles are proportional. Okay, so the sine of the angle and its side are proportional to each other. So the sine of angle A over little a is equal to sine of B over little b, the sine of angle C over little c. Those are all equal to each other. Now, another way that you could write this, I find that this version right here is helpful if you're trying to solve for the unknown angle. But if you're trying to solve for an unknown side, then I find it's often more convenient to have the unknown side in the denominator. And it should make sense that if we take the reciprocal of one part, we take the reciprocal of all of the parts, and that should create an equivalent formula for us. So there we go. Now, another thing that I want to mention is that we're usually not looking at all three of these components at a time. Usually we're looking at maybe two of them in isolation, right? So maybe, for instance, I have in this scenario here, I have 3 of the unknowns out of 4. I'm solving for the fourth. All right, I think the best way to help you understand how the law of sines can be applied is to look at an actual problem. So let's do that next. So again, when you don't have a right triangle, we cannot use SOHCAHTOA. We have to use the sine law or the law of cosines, which is coming tomorrow. All right, so let's look at this example here. I'm going to read it with you, and I'm going to take you through it. So it says, in triangle RST, they're giving us that angle S is 83 degrees, side little r is 53 meters, and angle T is 26 degrees. And it says solve the triangle. So you'll remember in previous lessons that solving the triangle involves finding the measure of all of the sides and the measure of all of the angles. A good strategy to start off with is to draw this triangle out, and so I'm going to do that. So let's just draw, and again, I'm not really worried too much about it being to scale. I'm just gonna, just sketch out a diagram. And so I'm gonna label my corners as R, S, and T, labeling my vertices. And then I usually go ahead and I will label the opposite sides with their lowercase versions. And that helps me to relate the sine law. Now what I'm going to do is I'm going to go ahead and fill in the information that I have about each of my, from the question. So it's telling me that angle S is 83 degrees. So I'm going to go ahead and fill in 83 degrees. It's telling me that R is 53 meters. So I'm going to go ahead and include that in as 53 meters. And angle T is 26 degrees. Well, I haven't drawn the best diagram here, folks, but that it is what it is. I'm still going to be able to use this to solve the problem. So here's my 26 degrees. So obviously not very much, not to scale. All right. So now it's asking me to solve for this triangle. So I can kind of start with whatever I want to, but in using the sine law, I know that I can solve for an unknown side here. I think what I'm going to start with is I'm going to solve for what I think is probably the easiest part of this, which is angle R. And I want you to think about why that is. Well, hopefully you're remembering that all of the angles in my triangle have to still add up to 180. So that if I know that, and I know the measure of the other two angles, I can say, well, 180 degrees minus the measure of angle S, and then minus the measure of angle T. And then I can easily solve for R. Angle R. So go ahead and do that. I am going to do the same thing. And I am getting 71 degrees. So there I go. I've solved for angle R. So I've done one part of this question. Now, I should remind you, and I didn't mention it before, that again, we also cannot use Pythagorean theorem for a non-right triangle. So we are going to have to use our sine law in this case. So, the sine law does a great job, as I mentioned, of relating side lengths to angles, right? So in order to use it, I need to look and see, well, which of the sides have I been given? I have been given side R, which means that I'm going to need to know the measure of angle R. And since I did that, and it was 71 degrees, I am just going to go and fit that in to my diagram. And so the sine law will allow me to relate angles and their opposite sides. I'm going to go ahead and for my second step here, I'm going to call this step number 2. I'm going to create my sine law and I'm going to solve for side little s. So to do that, I'm going to write out a little statement about my sine law. So I know that side little s over the sine of angle big S is going to be equal to the side length of little r over the sine of angle big R. And that's all. And so I just need to make sure that I have all of the pieces of information. And remember, to solve a formula where I have a bunch of unknowns, all of them have to be known except for the one variable that I'm trying to solve for. And so in this case, what I'm trying to solve for is little r. No, I'm not. I'm trying to solve for little s. And so I need to make sure that I have all of the other pieces of information. Well, do I have little r? Yes, I do. It's 53. meters. Do I have angle S? Yes, I do. Angle S is something I have. Do I have angle R? Yes, we solved for that, so I'm good to go. So now all that I have to do is I have to go ahead and substitute all of my information in. So what I'm going to do is just make this a little bit smaller and go ahead and solve for it. So S over the sine of angle S, and angle S was 83 degrees, is equal to R, which was 53 meters, over the sine of the angle opposite it, which was 71 degrees. So now I'm going to bring my sine 83 upstairs and multiply by it. So little s, the length of little s is going to be 53 divided by sine 71 degrees times the sine of 83 degrees. Do a double check to make sure that your calculator is in degree mode before you do anything else. And that's just a good habit to get into when you're working with trig. I'm going to go ahead and type this into my calculator as well, and let's see how it goes. So typing in 53 divided by, I have a backwards calculator, so I have to type in my 71 first and then sine. I usually go equals after that for some reason, and then I'm going to go times 83 and then sine equals. And so I'm getting, when I round to the nearest, and the question didn't specify, so I'm going to just choose to round to the nearest whole, and I'm getting 56 meters. So there I go. So the measure of little s, I can now even input into my diagram as 56 meters, because now I know that. So I'm almost done solving my triangle. What do I need to solve for next? What's missing? Well, I'm missing side little t. So that is the last little piece that I need. I want you to go ahead and try to solve for little t. And if you're not quite ready for that, feel free to stick around and I will solve it with you. So remember that the law of sines, I'm going to call this step number 3. The law of sines works with angles and their opposite sides. So if I want to solve for side little t, I need to have angle t as part of my setup. So I would say little t over sine of angle big T is equal to, and now I have choices because I have all of the other pieces of information. So I can use either the information from R or from S here, and it doesn't really matter. I tend to use the information that is given to me in the problem as much as possible. And so I would, because I'm fairly confident about angle R, and I was given little r in the problem, I'm going to go and use the information for R as opposed to for S. But if I've done S correctly, there's really no difference there. All right, so there I go. I'm going to go R over sine of angle big R. Now I'm going to fill in my information. So T over, make this a little bit smaller, T over sine of 26 degrees is equal to my 53 over sine of 71 degrees. So again, I'm going to isolate my t by bringing my sine 26 upstairs, and that will give me t is equal to 53 over sine 71 degrees times sine of 26 degrees. So when I work that out, I'm getting 24.57 blah blah blah. So I'm going to round that to the nearest whole and say that t is equal to 25 meters. So there, I've done it. I've solved this triangle, found all of the side lengths and all of the angles. let's try a different question, one that we're going to need to approach from a different perspective. All right, so let's look at another example. I'm going to get you to start this one off on your own and then see how you do. So it's telling me that I have a triangle that is an acute triangle DEF, and they're giving me angle F, they're giving me little f, and they're giving me little d. And it says solve the triangle. I want you to round each length to the nearest meter and each angle to the nearest degree, just to give you a sense of things. So what I want you to do is to pause this screencast and to draw a diagram of the problem. Okay, I'm going to go ahead and start this again, not to scale, just strictly a diagram so that I can input some information. So, you know, it's not even a great triangle, but it doesn't really matter because all I'm doing is simply creating something to start with. So I'm going to go D, E, F. And so it's telling me angle F is 35 degrees. It's telling me that little f, okay, so here is little f, here's little d, and here's little e. It's telling me that little f is 42 meters, and little d is 64 meters. And so again, I want to remind you, this is not a right triangle. So unless they tell us that, or there's enough information for us to glean that, then we can't use Pythagorean theorem or SOHCAHTOA. So in this case, I'm going to use my law of sines. So now let's take a look at this. I need to solve for all of the unknown sides. To me, when I look at this, I would say that I probably want to use the information from F, big F, and then little f. And that's because I have the information for those two related sides. And so, well, what other piece of information do I have? The only other piece of information I have here is on little d. And so what I'm going to do first, and this is my plan, is I am going to try to solve for angle D right here. That's going to be my first thing that I'm going to do. Because I don't have the other angles to help me solve for little e. So it seems to me it makes sense to start with solving for angle D. Now, if I'm trying to solve for angle D, that means that the statement I want to make is this one. I want my sine of angle D to be in the numerator. Now, it doesn't matter really, but it's just going to make solving one fewer steps. So sine of angle D over side length little d is equal to the sine of angle F over the length of little f. And so now let me just substitute all of the values in there. So the sine of angle D is, of course, my unknown. Side little d is that 64 meters. And then I have the sine of big F. That's the angle that I was given, which was 35 degrees, over length of little f, which was also given at 42 meters. So I'm going to start with the same approach that I had with the last question, where I need to isolate sine of d, and I'm going to do that by taking my 64 and moving it upstairs, just to isolate, as we have in previous questions all year long. So now the sine of angle D is going to be equal to sine 35 degrees divided by 42 and then times 64. But the difference here is that when I go ahead and I substitute all of this information in my calculator, it doesn't give me angle D. It gives me the sine of angle D. So I'm going to take one extra step and just actually find the value of that. I'm going to make this a little bit smaller. And so the sine of angle D is going to be equal to, just typing all of this into my calculator, and I usually find if I can get this ratio to 4 decimal places, I usually am in pretty good shape. So I'm going to say 0.8746 0. That is what I get when I simply type all of this stuff into my calculator, so double check. Right, but that doesn't do me any good. I need angle D. So I'm hoping you'll remember from previous lessons that the button that I need to press when I'm looking for unknown angles is that sine to the -1 button, and so it's no different here. So I'm going to say I isolate angle D by saying that's going to be sine to the -1 of 0.8740. And if you're lucky, you have not cleared your calculator after doing this, because all you really need to do at this point is just to press your second function sine, and that will give you 61 degrees for angle D. So I'm going to go ahead and I'm going to input that here, so 61 degrees. What I want you to do is to pause the video, and I want you to attempt to solve for all of the other missing pieces. And so what are we missing at this point? It looks like we're missing angle E, and we're missing side little e. All right, so let's check in now that I've solved these problems. So what I decided to do was, this is an easy fix. I knew that the value of 2 of my angles, and so that allowed me to solve for angle E fairly easily by just remembering that my triangle sum has to be 180 degrees. So I got 84 degrees, therefore, for my angle E, which I guess I can go ahead and just put in here as 84 degrees. I love how accurate my drawing is, but whatever. So then, once I knew that, the only thing left to find out was, of course, side little e. And so I simply set up my sine law. I chose to use information about side and angle F in solving my problem. And when I did that, just substituting into my sine law and isolating side little e, I was able to get 73 meters for side length E. So hopefully those examples will help guide you through some of today's practice work, where you'll just learn how to set up and utilize the sine law to find unknown angles and side lengths. And as always, if you have any questions, feel free to reach out.